Hello again. Today we will discuss my process of designing a voltage regulator. In designing this voltage regulator, we are going to use an integrated switch mode power supply controller with high side switch. We're going to walk through the process of selecting that switch mode power supply controller, as well as making a schematic design using that controller in this video. Now before we head over to the computer, I want to talk about something that will guide this design from part selection to completion, and that's requirements. In this case, there are 3 critical requirements and then a few less critical requirements. Let's start with the critical requirements. In this case, I know that the switch mode power supply controller must be able to withstand a 24 volt input voltage, since that's what the LEDs require. This converter also needs to achieve a 6 volt output voltage, which will be later trimmed to 5 volts with our linear regulator. Thirdly, this converter needs to be able to supply enough current for our digital electronics to function correctly. In prototyping, I have had this design work successfully off of a USB 2.0 connection, which is limited to 500 milliamps. Therefore, I will design my 5 volt converter to supply 500 milliamps. I expect the actual current draw to fall somewhere around 100 milliamps. This brings us to our other requirements. In this case, it would be nice if our converter could also supply 12 volts on the output. This means that I can use the same schematic and layout design to achieve both the 5 volt output voltage and the 12 volt output voltage. It would also be nice if this package, or the package of the switch mode power supply controller, doesn't have a thermal pad. Without a thermal pad, that will increase solderability, especially when I'm doing this by hand. As a final optional requirement, it would be nice if the chip comes with a manufacturer's reference design. This will make it more easy to implement their IC successfully, and will reduce the time that I need to spend analyzing the design to ensure that it will operate with stability. Now with this all in mind, let's head over to the computer and dive into this design. Let's go. Now that we're at the computer, let's go ahead and run through trying to find our switch mode power supply controller IC that will meet the requirements that we just talked about. I'm going to start here on DigiKey's website, go down to ICs, then choose Power Module IC, DC to DC switching regulators. Alrighty, let's go ahead and choose step-down controllers, positive output configuration, topology, buck. This will get us started. Now, let's go ahead, set our requirements into these filters. Choose only active parts. Adjustable output. Now let's go ahead and browse these part choices. We have this narrowed down to some devices that should meet our specifications, able to achieve both 6 volt, 12 volt outputs, being able to handle enough current. Actually, looks like I forgot that one. Let's go ahead and apply that. Alright. So now that we have all of our filters applied, I have sorted this by minimum quantity from lowest to highest. This is because we'll be ordering in small quantity. If I also sort by unit price from low to high, here we can see a lot of good options. Many of these components have a thermal pad on the bottom of the package, and some of these do not. Since we prefer one of these devices without a thermal pad, it looks like there's this part here, this part here, and the part that we've selected. Let's go ahead and take a look at these. So it looks like in this case, this can output 1.2 amps, has a maximum input voltage of 24 volts, and a maximum or minimum input voltage of 4.5 volts. However, since this maximum input voltage is 24 volts, that means that there is no room for tolerance on our 24 volt input. That wouldn't make a very good choice. Let's take a look at this converter right here. Maximum input voltage of 26 volts, which leaves 2 volts of headroom from our nominal input voltage to when this regulator will be damaged, with a maximum output current of 1.2 amps. Let's go ahead and look at this converter that we picked. It has a maximum input voltage of 36 volts with that 1.2 amp output current. This is ultimately why I chose this variant from the otherwise same manufacturer. It's really just the higher input range, or higher input voltage range, means that there will be plenty of design margin to prevent this converter from being damaged. Let's open up this datasheet now that we've selected a switch mode power supply controller. On the front page here, I see a typical application schematic, which is one of our optional requirements. This chip does not have a thermal pad. It will be able to supply at least 500 milliamps, and we will be able to use one controller to achieve both a 6 and 12 volt output. Therefore, this controller looks like a good controller to use. Okay, looks like based on this typical application schematic, we'll need an input capacitor with 4.7 microfarad and an output capacitor with a value of 10 microfarad. We'll keep that in mind. These should be low ESR capacitors, so I intend to use ceramic capacitors with an X5R or X7R dielectric. Looks like we'll need to choose an inductor with a value of 22 microhenries, a Schottky diode, and this capacitor C3. Looks like we'll need to read into this datasheet further to see exactly which values we should use. We'll also need to choose R1 and R2 that will provide voltage regulation sufficiently. Care should be taken with these absolute maximum ratings and recommended operating conditions to ensure that your design will not overstress this part. Design margin for every one of these ratings is a good thing. That is, don't use a chip or capacitor or resistor to 100% of its rated value. Driving a part to its absolute limit will shorten your design's life and adds a potential for a point of failure that is completely unnecessary. Keeping in mind this thermal resistance of your package is also important. We already did a rough calculation of how many watts we expect our converter to dissipate. Ensuring that this converter won't overheat, considering it doesn't have a thermal pad, will be very important. Okay, so now we have output voltage, 6 volts, divided by 450 kilohertz times our inductance, 22 microhenries. All right, this quantity times 1 minus the output voltage divided by the input voltage. We'll use nominal values for that voltage. So this is delta IL. And now IL peak should be our output current. In this case, we'll assume half an amp plus this value divided by 2. So in this case, we should size our inductor to handle at least 0.7 amps of current. Overall, this converter looks like it will satisfy our requirements. Gave some quick formulas for helping us size these other supporting components. And we'll go ahead and get to this voltage ratio in a second, but first we need to figure out what we need to do to find C3. Let's search for C3. Only get one result. Alright, let's continue reading here. Here it gives pin name BST and says to connect a 100 nanofarad capacitor. Let's go ahead and search for BST. Well, looks like I can't find any other comment about this, so we'll make a note that we need a 100 nanofarad or 0.1 microfarad capacitor. Now let's try to find our inductor on DigiKey. We need a fixed inductor with a value of 22 microhenries. Let's start there. And we need a saturation current that exceeds the current that we just calculated using the datasheet, which is 0.72 amps, 720 milliamps. So we'll start at 750 milliamps and move on up to the maximum rating of our converter. To improve EMI performance, we will not select an unshielded inductor. We'll choose cut tape and sort by price. Looks like some of these aren't rated to handle enough current for our design. Let's fix that. Here is the inductor that we selected. This is the inductor that is currently used in the design. Looks like the unit price is 29 cents as opposed to 34 cents. And it looks like this inductor is rated for 720 milliamps. And in this case, I set my minimum current to 750. Let's include 720 milliamps here. That's still more than the 500 milliamps that we expect, but doesn't exceed the rating of our chip. Looking here, now we can see the 29-cent inductor that I chose for the design. Notice the part number is the same. Okay, perfect. We found an inductor that will meet our needs. Let's walk through that same exercise with our Schottky diode. Average rectified current, 700 milliamps, up. We want a surface mount part, active, Schottky diode. cut tape packaging. But 24 volts should be sufficient. Therefore, I will choose 30 volts and up. Let's choose low forward voltage components. Let's say less than half a volt. Alright, here we're starting to see some very suitable looking components. Let's see if the part that I selected is in this list. So, taking a look at this list, sorting by minimum forward voltage, it looks like getting around 400 millivolts is where we're starting to see some economical selections. In this case, the surface mount pads are away from the device and not underneath the device, improving solderability by hand. This is ultimately the Schottky diode selected in my design. However, electrically speaking, all of these search results would be sufficient. Minimizing forward voltage will improve efficiency, but these components cost at least 12 cents more, or almost 1.5 times the cost of the part that I selected. There's a balance to be made here, and electrically sufficient is just that. There's no need to buy a better component than what you need, considering your load currents and the requirements for your design. So starting, we have Vout equals 0.8 times 1 plus R1 over R2. Putting in our output voltage of 6 volts, 0.8 times 1 plus R1 over 5 kilo ohms, dividing both sides by 0.8 gives 7.5 equals 1 equals 1 plus R1 divided by R2. Subtracting 1 from this side of the equation gives 6.5 equals R1 divided by 5,000. Multiplying by 5,000 gives 6.5 times 5,000. 6.5 times 5,000, which is 32,500 ohms equals R1. Alright. I would go through the same process for this 5 kilo ohm resistor, input and output capacitance. We've already selected our inductor, our controller, and our diode. So that was part selection for the 6 volt buck that will take our 24 volt input and convert it to 6 volts, which can be later trimmed to 5 volts with the linear regulator. Today we were able to talk about the steps I took to implement a switch mode power supply using an IC with a reference design and specs given in a datasheet. We modified the reference design to suit our application and stepped through how to select orderable part numbers. In the coming videos, we'll build on these concepts by discussing some of the theory behind current regulation, stepping through this design process again with a current regulating switch mode power supply. If you'd like to learn more about switch mode power supply theory or selecting orderable part numbers, let me know down below. I hope that you learned something great today, and I hope to see you again soon. Bye!